and welcome to our webinar session for today. Today we will be discussing the topic energy profiling and management with Fronius Inverters. Today I'm joined by my colleague Cyprian Okolo, our technical sales advisor for Western Africa based in Lagos, Nigeria. And myself, David Mwangi, I'm the technical sales advisor for Eastern Africa. And together we are going to be taking you through the course of today's webinar. Just to give you some brief information on the responsibilities of the various technical sales advisors in Africa. If you are located in any of the areas that are supported by either Mohammed Sidat, Cyprian, or myself, then there are all the areas color-coded green, blue, as well as red. So for the Southern African area, all the green coded countries, you get in touch with Mohammed Sidat. Then for the blue coded countries in Western Africa, you get in touch with Cyprian Okolo. And then for the red areas, you get in touch with myself, David. In addition to that, I would like to give you also some brief information on the various Fronius sales partners in Africa, whereby you can get our inverters and other products, in addition to also getting after sales support as your first line of support for your various installations. So in the sub-Saharan African region, we have quite a number of them. So starting from Inomatic, based in South Africa, IBC Solar as well in Southern Africa, Radio Electronic in Namibia, then One Stop Solar in Zimbabwe, we have Tino in Ghana, we have CAT in Kenya, Components in Ghana as well, in Nigeria, and Greenspark, Manda Power in Madagascar, and Knights Energy in Kenya. So for any inquiries regarding the purchase of inverters or any spares that you may require for your inverters, kindly get in touch with these sales partners. The agenda for today, we are going to be addressing the following. We will look at energy flow management. Then we go on to energy profiling. After that, I will go into load management, after which I'll hand over to Cyprian, who will do the required settings and commissioning, and then the reference system is going to take you through that, as well as the load profile design. Get started and look at energy flow management. So from the Fronius perspective, we start, of course, with a PV system that has a smart meter and a data manager. So because these are the key requirements for you to be able to do load profile analysis. So the next step would be, of course, to be able to control heavy loads that might be connected or consuming energy in your system. And therefore, we go into the area of load management. And after that, we also advance into an area whereby not only managing these loads, but also storing a bit of the energy for later use. And this storage can either be in the form of a battery storage or in the form of hot water. So the hot water and the battery storage are, of course, sections that can be covered entirely in different trainings. But for hot water, we go through the on-pilot. And for battery storage, at the moment, we are working in conjunction with BYD, HVS, HVM batteries, as well as the Fronius Gen 24 Plus hybrid inverter. So therefore, this gives us an illustration of how this Fronius energy flow management can happen, starting with your generation, and then you go on to SOLAR.WEB and analyze how the energy flow is happening with your system, and therefore looking at load management and saving of energy, how this therefore can be optimized. In terms of the control options for the various loads, we have two possibilities. So we have one that is geared purely towards load management, and this can be achieved using the digital IOs to switch on the loads. And the key target here would be to increase the self-consumption level, and therefore you turn on this load, or you reduce the peak loads, and therefore by turning off some specific loads that would cause your energy or power consumption to peak unnecessarily at some point. The other alternative for control would be the dynamic power control. And a good example here would be the stepless control of surplus power, maybe for storage in a battery system or for storage in hot water using the Fronius on-pilot. And therefore, the key target here would be to increase the self-consumption as well as the self-sufficiency level by also avoiding peak loads in combination with your battery storage. And Cyprian is going to be covering how to avoid peak loads in combination with the battery storage later. So let's now get into energy profiling. In terms of the energy profiling, what we imagine would happen is a scenario whereby it would be possible to make use of several Fronius smart meters in one setup. And therefore, one alternative would be whereby you have a combination of maybe a Fronius on-pilot, as we see here, option 1, and 2 extra secondary smart meters, as we refer them. Because in this setup, there is required to be at least one primary smart meter. The other alternative would be in the absence of a Fronius on-pilot, then you have 3 secondary smart meters, as we see here in option 2, in combination with the primary smart meter. Therefore, meaning that in this setup, we have a total possibility of having 4 Fronius smart meters in this installation. So the question could be why we need all these smart meters. So as we can see down here, we have some dedicated loads, or a generator, could be a wind generator, or a PV system that is using a third-party PV inverter. And you want to have the production of this in the Fronius SOLAR.WEB for monitoring and profiling. And therefore, you track the production of that third-party generator using a Fronius smart meter. It could be also that you also want to monitor something like a pool pump and look at exactly how this pool pump is utilizing energy within your setup. And therefore, this gives us now the possibility to do very precise energy profiling of the various loads and appliances that are connected to this setup. However, there are some restrictions in terms of the total number of smart meters that can be used in one system. And the major restriction here comes in the form of the Modbus addresses that are available with the concerned inverter. So the number of feasible smart meters that we have said it's possible to have a maximum of 4 has a more stronger restriction with the Fronius Seymour hybrid as well as the Fronius Gen 24 Plus inverters, because these inverters must reserve, if they are used together with a battery system, must reserve at least one Modbus address for use with the battery storage. And then, of course, if you bring the on-pilot into the picture and you're connecting the on-pilot using Modbus RTU, then Modbus will also take up one address, as you have seen in the previous example. And therefore, the maximum number of Fronius inverters is going to be limited to a maximum of 3, including the primary smart meter and the Modbus channel for the on-pilot. However, this table below here gives us now a more specific overview in terms of the number of Fronius smart meters that are possible, both the primary and the secondary. And we are considering an inverter with the Fronius DATAMANAGER 2.0, and also a similar inverter like the Fronius Seymour hybrid with a different card that we refer to as the hybrid manager, or maybe the Gen 24 Plus inverter. So if we do have an installation without a Fronius on-pilot, we can have a maximum of 4 smart meters in an inverter with the DATAMANAGER 2.0. And if we have the SIMO hybrid, we can only have a maximum of 2 smart meters. For use of the on-pilot, connecting to the inverter using Wi-Fi or terminal control protocol Wi-Fi, then still we maintain the same number of smart meters for the data manager 2.0 inverter operating with that data manager. And also for the SIMO hybrid, we still retain the number possible of 2 smart meters. However, if we connect the Fronius on-pilot using Modbus RTU, then even for the inverter with the data manager 2.0, we must then reserve one Modbus address for the on-pilot, meaning that we are going to have a maximum possibility of 3 smart meters in the setup. And then for the SIMO hybrid, we are going to have the possibility to run only 1 smart meter, and therefore in this case you're going to have only 1 primary smart meter if an on-pilot has been used through Modbus RTU. In terms of the settings, when you're adding the various smart meters in your setup, you do this very easily by accessing the configuration area of the Data Manager web user interface. And once you have gone to the web user interface of the Data Manager, then you access the submenu meter section. And within this submenu of the meter, you can then add your primary meter, as we can see here, and then also you can add the various secondary smart meters that you're using. When all these have been added, then you can also see a list within the web user interface of the data manager. And this is going to tell you what each of these smart meters is doing and also the location of the smart meter. So for instance, we can see that the very first smart meter used is a primary smart meter that is at the feeding point. And this is now the smart meter that has to take overall control of the setup, because it also knows the balance of power that is needed by communicating with the data manager in terms of how much the loads are consuming in total, and therefore the balance that has to come from the grid. Then we have another smart meter that is a generator smart meter. So in this case, we are having an external or a third-party generator. It could be a wind generator or a PV inverter. And therefore, in terms of also here, we can see that the position or the category we are talking about is a photovoltaic inverter plus a storage unit. And then you also have a third smart meter in the consumption path, therefore meaning that this is controlling an additional load in the setup. And in this case, we are controlling a heat pump using the third smart meter. So you can also see an illustration or a schematic of the arrangement of the smart meters. And therefore, you can know exactly from the Data Manager web interface how many smart meters are already configured for use within the setup. In terms of the visualization and how the setup would look like in Fronius SOLAR.WEB, we can see that for every smart meter that has been added, then every one of those smart meters is going to appear in SOLAR.WEB under the energy meters category. So you basically access this by going to your system in SOLAR.WEB, then go to settings, and then access the components submenu. And from this components submenu, then you can access what are the data source IDs for that particular system. So in this case, we have 2 data source IDs, and these are basically data manager IDs that we can see. So in this setup, we have 2 data managers that are sending data to SOLAR.WEB. And in addition to that, we have other 4 smart meters within the setup. So we have 1 primary smart meter, and we have 3 secondary smart meters within the setup. In terms of the visualization and how this data therefore is displayed within SOLAR.WEB, so this is available in both the history chart, the analysis chart, as well as in the reports. So in this case, we have, once you have created the channels that you want to get reports for within the history section of SOLAR.WEB, then you can see a graphical representation of what is happening with the various smart meters integrated into the system. And therefore, the analysis, also the load profiling that you're talking about today, becomes very, very easy once you have this graphical representation of data within SOLAR.WEB. In addition to that, you can see exactly the combination of the various smart meters, and therefore you're talking about consumption as well as production. So in this case, we have two inverters, and these inverters are an inverter SIMO 4.5 and as a SIMO 8.2 inverter. And these two are producing, as we can see, on the production scale from 0 to 50. So we can see what each inverter is doing. And then in terms of consumption, we can also see a very good representation, including also the on pilot, what each of these consumers are taking out of the balance of energy that is available in your setup. So in terms of load management, this is also critical to understand how Fronius inverters enable you to do this. So we are starting, of course, with an inverter that has the capability to control what we refer to as the digital IOs. And the digital IOs are then working in conjunction with an external relay to switch on or off a load depending on some predetermined thresholds. So one of the key things that you might want to do is with the load profile analysis is the peak load management. And therefore, in this case, we can see that with the communication from the smart meter, because the smart meter keeps an eye on the overall consumption in your setup, then you're able to manage your peak loads. And these peak loads is going to be managed, as we said before, by allowing the digital IO from the inverter to switch on or off a particular load connected to it, depending on the available energy within the setup. And if you want to, for instance, avoid drawing too much power at some specific periods of the day, whereby you could also be incurring extra charges depending on the peak loads. So therefore, the required components for you to be able to achieve a proper load profile analysis and therefore load management would be a Fronius inverter, could be a Fronius Gen 24 Plus inverter or a Snapinverter, a Fronius smart meter as well, and then you have the capability to access the data for analysis within Fronius SOLAR.WEB. So one specific example for load management would be in a residential setup, whereby we have a wall box controlled by Fronius load management. And in this case, we want to avoid or to do a 5 kilowatt peak shaving so that we are not consuming loads or power that is in excess of 5 kilowatts at any one particular moment. And in this case, we can see that during the period when the EV charging system is operating, and we have other loads that are also consuming power within the setup, if the total consumption is to exceed the 5 kilowatt peak, then the Fronius inverter, through the load management option digital IOs, has the capacity to switch off the EV charging so that the peak consumption here does not exceed 5 kilowatts. Because as you can imagine, if you look at this red area that has been taken off here for EV charging, and you add it to the gray area that is the other consumption that is within the setup, this would have easily gone above the 5 kilowatt peak. And therefore, this means that if you incur charges depending on peak energy consumption, this is one of the ways to avoid these peaks of energy and utilize most of these appliances when you have generation that can sufficiently cover the consumption from the PV system. Another example would be a load management scenario within a commercial office, and therefore designing the PV system to cover all the loads, including the air conditioner on a sunny day. And then this also is looking at the integration of 2 EV charging points, which is about 22 kilowatts maximum each. And these are also controlled by the Fronius load management output. The target in this scenario is to avoid any peak loads that are higher than 50 kilowatts. So the way we achieve this is that anytime that we are going to approach a consumption of 50 kilowatts in combination to the other existing appliances that are consuming, then through the Fronius load management output, we have the possibility to either reduce this consumption or switch it off completely so that we do not have it exceeding this limit of 50 kilowatts. And this could also be very, very useful if you do not want to change the existing infrastructure as far as wiring is concerned and the control gear within the setup. So therefore, you can have a very intelligent way of knowing that I have a control gear that can trip at maybe 50 kilowatt or thereabout. And therefore, if I see the potential for my load consumption to be anywhere near 50 kilowatts, then using the Fronius load management outputs, you can easily get rid of such a problem by either reducing the consumption of that particular load or switching it off completely. And therefore, the target here has been achieved by turning off one EV charger or using an EV charger that has integrated load balancing within it. So therefore, we can see that during the entire load cycle here, the peak of 50 kilowatts has not been exceeded by the intelligent control that is possible using the Fronius load management options. So therefore, the question can be, and most people will ask, why do I need to manage my peaks? So why is peak load balancing important? So a few points to clarify this would be avoiding higher consumption costs. So this could be for customers, like I have mentioned, who have peak load measurements, and therefore they are charged extras depending on the peak consumptions that they have. Then also you have the possibility also to avoid high costs of network adaptations. Like I've mentioned also, you want to be sure that you can retrofit some kind of intelligent controls into a system. You can add additional appliances into your setup, but also have the possibility to maintain the existing wiring and control gear infrastructure without major changes. And this is only possible by, for instance, adapting the load control possibilities within the Fronius inverter setup. Another important point that we can mention is the possibility of higher EV charging power for those who are going to start enjoying electric vehicles. In other parts of the world, this is already a common thing. So integration of PV and battery storage are going to be able to give you or guarantee you even higher EV charging power capabilities in conjunction with load management options within the Fronius inverter setup. And therefore, in a nutshell, this is what we refer to within Fronius as the energy flow management of the Fronius inverter. So from here, I think my part is finished, and I'll be handing over to my colleague Cyprian, who will take you through the next session of the webinar. So Cyprian, if you can take over from here.
Yes, indeed. Thanks a lot, David, for your wonderful presentation. I believe we can all see my screen and hear me clearly as I continue from this point where we shall be discussing the required settings and what is needed for commissioning in terms of, or as long as energy profiling is concerned. And we shall also take a typical example of how to do, how to size a system using the energy profiling. Great. But before I start, I would like to launch a poll question, and hope all give the respective responses. I'm going to launch it right now, so I believe we can see it. So the question is, apart from the Fronius energy and load profile management, how do you usually achieve load profiling and energy management? So the options are by manual observation and calculation. Second option is the use of grid meter readings or other manufacturers' algorithm. And then lastly, not using any analysis. So these are three options, and I would like us to respond to this poll question, and we'll be continuing after I have shared your responses. So I'll leave it on for, say, about 10 seconds, and then I believe that should be enough time for us to respond, and then I'll be sharing your answers. Thank you very much. I will be closing the poll question pane now, and then share your responses. So as you can see, we have 38% going for manual observation and calculation. 25% of the attendees chose the option that they normally use, grid meter readings and other manufacturers' algorithm. And then 38%, equal to the first option, say they don't use any analysis. Okay, thanks a lot for your responses. And I believe that by the end of this presentation, we would be much more informed and be able to take an informed decision afterwards, provided with the information that we will be providing. Great. Thank you once more as I now continue with the presentation. So in terms of settings and commissioning, we'll first of all take a look at the components that are required. Of course, you would need your inverter. It could be a Fronius Gen 24 Plus inverter, it could be a Tauro, it could be a Snapinverter. In the case of a Snapinverter, please ensure that it's a Snapinverter that has a DATAMANAGER integrated, because that is the communication card or the data communication component in the inverter. So without it, there can't be any communication. So, but for the Gen 24 Plus and the Tauro, it's already integrated. So by default, so no need to worry about any additional components for communication. But for the Snapinverter, as we would know, we have the light versions and we have the full versions. Full versions are the ones that have the DATAMANAGER, while the light versions are the ones that don't have DATAMANAGER. Great. So, and of course, you will need a Fronius smart meter to help you get a wholesome coverage of both consumption and production. And then, of course, you would need your relay, usually 12 volts relay, because the output of the input-output port of the DATAMANAGER is the 12 volts signal. So you would need a 12 volts relay in this case. Some might prefer to use contactors, but just ensure that it is a 12 volt rating. Good. So taking a closer view for the Snapinverter, this is how it looks like, just underneath the inverter. So a closer look at it would reveal the input-output ports. So there are 4 usable input-output ports, and these input-output ports can now be configured as output ports. So yeah, so they are input-output port 0 to 3, that is 0, 1, 2, and 3. Okay, so a look at the Gen 24 Plus inverter. Same here, we have 4 input-output ports, 0 to 3, that is 0, 1, 2, and 3, just like the Snapinverter. Good. And next up, we take a look at how you can do the mapping, because if you don't do the mapping on your web interface, it's not going to be integrated to the hardware of the inverter. So this is on the web user interface, this is where you can actually do the mapping of the input-output ports you're going to use. So here you can select the input-output port terminal that you want to use for a particular purpose. And then once you select it, please ensure that you click on, or you click on this tick mark. So because without ticking it, it's not going to save. So once you tick it, it will automatically save your settings on the input-output mapping. So please don't forget this particular instruction. And then after the input-output mapping is done, of course, like I told you, we have 4 of them. So you can program each of them for different purposes. You can say program input-output 0 to control your air conditioner, input-output 1 to control your water pump, and then, you know, like the likes. So that's basically it. And of course, the provision is made for you to actually tag them by the name of the component or appliance that you want to control. So after this is done, you will now go to load management. That will be seeing that in the next slide, as you can see. So here is where you now include or set the conditions that should be met for these appliances to either come on or go off. And before I continue, this is also to tell us here that it is possible to set the priorities of how you can manage your surplus energy. From this example, as you can see here, load management IOs has been set on the highest priority, which is priority 1, followed by the battery, and then the on-pilot. So from this particular setting, using it as an example, what this means is that once you start generating more than you're consuming, meaning that you have surplus, it is going to give more preference to load management IOs, meaning that it is going to trigger the support or triggering heavy loads that you have already pre-configured, first of all. And then if there is enough surplus energy to take on the next priority, then it will now bring in the battery. Otherwise, it will ensure that the cycle of the load management is complete, meaning that it has gone through its control cycle before the next priority can be taken on or can be triggered, and then continuously till the third or the last priority or the lowest priority. So it now behoves on the design engineer or the client or the client's wants to determine which of these energy management priorities would be much more important, and then putting it in order of preference. So you could have, this is of course interchangeable. So you could have your battery as priority 1. So meaning that once you have a surplus, it will first of all start charging the battery. And then afterwards, if load management IOs comes in as priority 2, it will now, once the battery is full, it will now trigger the load management priority. So that's it. And then coming down to what I was explaining earlier, this is where you pre-configure the conditions necessary for your input-output ports to be triggered. So for this particular setting, it's actually targeted at achieving high self-consumption. So in this case, you would need to set the figure and mind you, to start with, you can actually, it can actually be triggered either by power production or by power surplus. And so for achieving high self-consumption, of course, going by power surplus is, of course, the right choice to make, meaning that it is only when there's a power surplus that it can be triggered. So now, what level of power surplus are you targeting? So in this case, 1.1 kilowatts or 1,100 watts has been set as the power surplus feed-in figure. It means that once the power surplus hits this figure, that is 1.1 kilowatts, it triggers it on, it will turn it on. And then the turn off condition, as you can see here, is when the consumption, when the base load consumption hits 100 watts. So of course, this can be configured to the specified figures according to the load profile. And that's not the only way to configure it. We can also set it to function to given duration. So you can actually have it to function, say, we have a minimum of 1 minute and I think a maximum of 1,500 minutes. So you can actually program your appliance to function for a particular duration. And then not just that, you can also program it to function for a particular duration per day. So these are all programmable on this part. So, and once you're done, please ensure that you click on this tick mark. Great. So this was for achieving high self-consumption. Now this is load management function to achieve peak load balancing. So it is slightly different from the previous setting. So what we should be targeting here is, of course, you can set the figure that a surplus needs to meet before it turns on. So once that is done, you would now have to set the figure that your consumption must not exceed. So if you set 3,000 or 3 kilowatts in this case, it means that once your consumption hits 3 kilowatts, it is going to turn off. So that's basically what this setting is all about. Of course, these are for setting for Snapinverters. And for Gen 24 and Tauro inverters, of course, this can be achieved by using the Solar Start app, which is available and downloadable on our app stores. Here, once you get into the pin, the load management pin configuration, you can now have access to the 4 input-output pins that you would have to configure to achieve your load management function. And then setting of threshold, the same thing applies. In this case, you select by power surplus and then set the figures that would warrant triggering on and then triggering off, as you can see. Good. And then in this case, we're going to take an example of how peak load balancing actually occurs. We'll be using an example with an electric vehicle charging. So in this case, we have settings of a threshold with PV surplus activation. So from this graph, we can see that the triggering point for the surplus PV activation is 2 kilowatts, as you can see. And then the off threshold is 4 kilowatts. It's in negative because we're consuming. So since we're consuming, we're of course paying. And then that is why it's on the negative plane. And then of course, the EV charging power capacity is 3 kilowatts, as you can see from this power stamp. From here to here is 1, 2, and then 3 kilowatts. So from this graph, this means that once your surplus power hits 2 kilowatts, the EV is going to start charging, and it will continue in that manner until your consumption hits 4 kilowatts. If your consumption hits 4 kilowatts, it will automatically stop the EV charging, so as to limit your consumption to that particular threshold. So this is, of course, for PV surplus activation, meaning during the day when there is PV power generation. So what happens at night? So at night time, the trigger is usually the base load. So for this example, the base load example of 500 watts is used. So this means that once your base load hits 500 watts, your EV charging starts, and then it will automatically turn off when the consumption hits 4 kilowatts. So that's basically how the programming helps you to save or not to consume too much energy in charging your EV or maybe supplying power to any heavy load. Good. So to buttress what we've been discussing all this while, we're going to use a reference example for a case where we have the same EV without battery storage. As you can see, we can notice here that there is an interruption in charging. To see this clearly, we have actually mapped in an alternative, say an equivalent graph, but this time around it's the grid power consumption graph of the same profile. So in this case, we can see that the charging was interrupted at this point. This happened because looking at the equivalent graph here, the grid power consumption graph, we can see that the 4 kilowatt limit was reached. So that is why the charging at this point was interrupted immediately. And then as you can see, it's continued once the grid power consumption was reduced or got reduced to a lower figure, as you can see. So that's for case without battery storage. Then in terms of a situation where you have battery storage, it makes the issue a bit simpler. In the sense that, as you can see in this case, the grid power consumption is relatively quite minimal, as you can see from the portion colored red. And this is so because the battery is called into play to kind of balance the peak load consumption. So as you can see, the regions colored yellow, which signifies or represents the power consumed from the battery. So it steps in at any point that there is a peak load consumption. So instead of taking it from the grid, it is taken from the battery. And then when it exceeds the battery capacity, it now takes it from the grid. And as you can see, it actually has very, very minimal values. Great. So with all this, we can of course say that Fronius comes with a lot of advantage when it comes to energy profiling and management, as it helps in avoiding high consumption costs for customers with peak load measurement. It also helps in avoiding high network adaptations, just like my colleague David has mentioned earlier, because you don't need to add any network of cable or fuses, no. And of course, by the use of standard components, like the Fronius Snapinverter with the DATAMANAGER, of course, Gen 24 Tauro, and the use of a smart meter and the 12 volts relay, you can actually achieve this. So the components to be used are not really complicated. And then, of course, you always enjoy Fronius support hotline for cases where you have questions and inquiries. Great. So having said that, we're going to go through a typical load profile design, where we're going to size an entire system by taking note of the load profile of the client or the consumer per se. So in order to achieve this, 4 points or specifications need to be taken into consideration. These are the energy consumption during the day, energy consumption at night, peak load current, and then of course, average load current. It's been observed that in most times, design engineers tend to mostly use average load current for regions that usually have unstable grid supply. Once this is done, it will be noticed that at some point you would have tripping, power tripping, because of the fact that the average load current, which is much, much lower than the peak load current, has been used for the calculation. Having said that, this implies that for regions or for system calculation that don't enjoy or have unstable grid supply, please ensure that you use the peak load current for your calculations. But if you have steady grid supply, please ensure that you use the average load current for your calculation. It will suffice. The peak load current is mainly meant for use in cases where you don't enjoy steady grid supply. So going forward, we'll now take a typical example. And in this case, we need to design a single-phase grid-tied PV system with battery storage. So from this first sentence, we've been given a clear idea of the system we're designing. First off, it's going to be a single-phase system. It's a grid-tied system. And of course, it comes with battery storage. So these are the three cardinal points or information that we're going to be using in order to achieve self-consumption of higher than or greater than 90%. So in this case, for this example that we've mapped, we are going to be considering three load categories. Load one is usually the average load that runs continuously throughout the entire day. And then we have the second category, load two, that runs for short periods across the day. And then we have load three, which also are heavy loads that run for short periods, but on a higher frequency than load two. So this for load two, it could be a geyser, which is pretty common in South Africa or Southern Africa. It could also be an air conditioner, say particularly common in tropical regions of Africa. And then load 3 could be a water pump for water supply to the house, or maybe a pool pump per se. So, but we have taken this as a template for you to give you a clear example of how this can be done. So as we can see, we have a timestamp of 24 hours here with the respective power consumption. So for the colored green, the power consumption colored green is the average load, which runs continuously throughout the day, 1 kilowatts. And then load 2 is for the aircon or geyser, which runs 3 times daily for 1 hour, duration. And it was just this, like I said, this is a template, so you can now use this as a reference point and then superimpose your own calculations or specifications. Okay, so this runs 3 times a day, 1 hour durations as indicated here. And then load 3 runs for 20 minutes for every 3 hours. And it has an average capacity of 2 kilowatts. Load 2 is 1.5 kilowatts. So putting that on the graph, this is exactly how it would look like on a timestamp. Great. So how do we now go ahead with the calculation, provided that we've been given all this data? So the next page will give us a guide on how to do that, as you can see. So transferred the graph to this page so that it will help us to make reference. Now we're going to look at, we're going to calculate the daytime load. And daytime is basically, we've taken the period of 6 a.m. to 6 p.m. So if you take another step back, we can see that daytime load actually the period covered when the PV generator is functioning, and the night times are the period before and after that. So let's now continue with the slide. So as you can see from this timestamp, the energy consumed during the day is going to be 1 kilowatt, which is the average power, multiplied by 12. That is 6 a.m. to 6 p.m. So this is the time. So 1 by 12. And then for the load 2, which is a 1.5 kilowatt, it is going to be multiplied by 1 because it occurs just one time between 6 a.m. to 6 p.m. And then for the third load category, which is the motor, it occurs 1, 2, 3, 4, so 4 times. But in this case, it runs for 20 minutes. But then the SI unit for this calculation is the time SI unit is in hours, which means that we'll have to divide 20 by 60 in order to give us the time in hour. And by the time we do this calculation, we'll be arriving at 16.2 kilowatt hour. And then nighttime load, this is basically the period between 6 p.m. to 6 a.m., which covers an entire period of 12 hours. So nighttime energy consumption will be 1 by 12, 1.5 by 2, but following the period in question. And then in this case, 2 kilowatts multiplied by 20 minutes over 60, and then multiplied by the period or the frequency of occurrence, which is 4 in this case. So here we're going to arrive at 17.7 kilowatt hour. So now we have energy consumed during the day and then energy consumed during the night. Great. In order to calculate the peak load current, we would have to divide the power by the voltage, because P, which is power, is equals to current times voltage. So making current subject of the formula, it's going to give us power over voltage. And then calculating it for the respective loads, we will be getting a total of 19.57 amps. And then for the average load current, we will now be taking the period of occurrence of this load into cognizance. So for the average load, it runs through 24 hours. So that means that this figure remains the same. That is 1,000 over 230. But for load 2, which could be the aircon or the geyser, it would have to, the time or the duration or the period that it occurs would have to be taken into cognizance. So in this case, it is 3 hours divided by 24. For the motor, the same thing is applied, multiplied by 8 divided by 24. So in this case, we're going to get 6.13 amps. So we can see in this case that the average load current is 6.13 amps. So for a load consumption that has unstable grid supply, if we make use of this average load current, you might run into some problem after installation. So it is better to make use of the peak load current. As you can see, it covers for the load consumption for the entire 24 hours duration. Great. Now, after that, how can you now determine the number of panels that you would need, and of course the size of the inverter? So that's actually easy to obtain as long as you know the wattage of the panels, you know the efficiency figure for the panels, and of course the dimensions. Once you do that, you would now have to obtain the irradiation figure. So in this case, we actually took the irradiation figure for Joburg, which is 5.2 kilowatt hour per square meter cost per day. And then you can obtain the area, the entire area of the panel needed by dividing the wattage or the energy consumption per day divided by the efficiency of the panel multiplied by the irradiance per day for the period or for the location. Great. So if we go back to the previous slide, we will see that the energy consumption during the day is 16.2 kilowatt hour. So this will now be divided by the efficiency. The efficiency is 21%, which is the same thing as 0.21, then multiplied by 5.2 kilowatt hour, as you can see in this case. The answer you get, we're going to get 14.8 meters squared. So this now represents the entire area that is going to be covered by this 400 watts panel. So since we now already know the entire area that will be covered by this panel, how then do we know the exact number of panels required? So this can be obtained by simply dividing the area of panels by the dimension, the dimension of a single panel. So length times breadth of a single panel is approximately 2.1 meter multiplied by 1 meter, approximately, of course. So this will give us 7.05, and then approximating it to the nearest whole number will give us 7. So this means that we will be needing 7 panels for the execution of this system design. And then the area of a state. The area of a state simply means that, of course, the figure we've calculated here as a 14.8 meter covers the exact size or space or area that the solar panels would cover. But then you'll need some extra space for installation and maintenance. So usually we have a factor of 1.3 that is usually added or multiplied by the area of the entire panel to get the area of a state. And once that is done, 1.3 multiplied by 14.8 gives us 19.24 meters squared. So this should be the area, the least roof area that is that should be sufficient for the erection or installation of these panels. So having gotten the figure of the panels required, it can of course be used to get or calculate the capacity of the inverter required. So this can be gotten from this equation, that is the power capacity of the inverter is equal to the capacity of the panels, the entire panels, divided by the inverter ratio. Now at Fronius, we can actually go up to 150%, but we tend to recommend 120%, which is 1.2. So by the time you divide the multiplication of 7 and 400 watts by 1.2, we will be getting 2.3 kilowatts. Now, I'm going to show you a slide immediately as you can see, the figure we obtained here is 2.3 kilowatts. But then when you look at the next slide, we can see that the maximum current for 3 kilowatts, the primal Gen 24 plus, that is the 3 kilowatts, is 20 amps. And then if we could recall, the peak current is the figure of 19.57, if I'm not mistaken, which is too close a figure. So because of that, we shall be choosing or be selecting the 3.6 kilowatt Primo Gen 24 Plus inverter that has an IMAX or current maximum peak current of 24.53 amps, as you would see in the next slide and as indicated. So as you can see, we'll be selecting the 3.6 Primo Gen 24 Plus inverter for this particular design. So going back to the slide, I just put it in summary that we'll be going for a 3.6 Primo Gen 24 Plus inverter because its maximum current exceeds or is greater than the peak load current and of course the average load current. So I believe this is understood by all. So let's now continue. Having obtained the capacity of the inverter, let's now go for the size of the battery storage. The size of the battery storage can actually be gotten by dividing the energy consumption at night by the efficiency of the battery. So the efficiency of the battery, of the BYD battery, has been given at 96%, which is actually a very, very high, very good percentage. And then, of course, to obtain the battery capacity, we now divide the energy consumption at night time. If we could recall, it is given at 17.7 kilowatt hour. Dividing this by 96%, which is the same as 0.96, we will be obtaining 18.4 kilowatt hour battery storage size. But then if we now go through the exact that I've included here, you can see that there is no 18.4 kilowatt hour battery size. The closest size to it is 19.3. So this means that we'll be going for a BYD HVM 19.3 kilowatt size battery. So as you can see, we have successfully, with the load profile that we've gotten, calculated the system size, we've calculated the number of panels, calculated the area to be covered, calculated the inverter capacity, and of course the battery capacity. For now, Fronius is only compatible with the BYD HVM and HVS batteries, and we will update you once the information changes. So that basically brings us to the end of this profile calculation. Yes, so left for me to give you is a further information of how you can obtain or get operating and installation instructions that can be obtained from our homepage, www.fronius.com, and then you go to downloads. And if you want to specifically speaking, you can actually obtain or get all the webinars that we have hosted on our playlist by using or clicking on this link. It will just take you to our Sub-Saharan Africa playlist where you're going to get all the webinars that we have conducted so far. Of course, for further inquiries, please contact the technical sales advisor for your respective region. And then for other inquiries, you can contact these contact details as indicated. So this, of course, brings us to the end of our webinar for today. I hope you all enjoyed it. And I want to believe that you might have questions. Please continue to send them. We will be attending to them immediately after the presentation. And on behalf of my colleague, David Mwangi, this is us saying thanks for attending and goodbye.